Hello everyone and welcome. In this video we are going to explain the somehow confusing topic, which is called the discrete Fourier transform. The source of confusion for this topic is mainly due to the fact that most textbooks or YouTube videos explaining this topic do not really cover some important details, which are needed to enable others apply the DFT with realizing what is actually happening. What is the definition of the DFT? In simple words, the DFT is a way to convert any function in its time domain that is restricted by a finite number of points to its frequency domain. As we know from Fourier series that any periodic function can be decomposed to a sum of sinusoidal waves, when we convert this periodic function to its frequency domain. This means that we can see the amplitudes of these sinusoidal waves components with respect to their frequency. Let's see this image. The dark blue function is a periodic square wave function in its time domain, and all the sinusoidal waves behind it are the decomposed waves and the components of this original function. The sum of all these sinusoidal waves will give us back the original square wave function. And as we know, any sinusoidal wave should have an amplitude and frequency. If we convert our square wave original function to the frequency domain, then we can represent the amplitude or the peak for each sinusoidal wave with its frequency value. The Bn here shows the amplitude or the peak, and the Fn here shows the frequency for each sinusoidal wave. Again, to the DFT. The DFT actually works exactly on the same principle of Fourier series, except that our function in DFT is a set of restricted points, and that's why it's called discrete. Let us take a look how that works. As we can see here that our blue function is restricted by the first and last point in the time axis. Now the points in time axis are called samples, and they are separated by equal distances dt. So if we took dt to equals 0.001, and took the points from t equals 1, to t equals 4, that is a total number of 3001 samples. Now after we took these many points, the DFT is able to capture the exact and total full shape of this function in its time domain. What the DFT will do now is to transfer this discrete function to its frequency domain, just like what Fourier series did for the squared wave function. We should note that the sampling frequency or sampling rate is the number of samples we took per second in the time domain. And the sampling frequency equals the reciprocal of dt, which is the spacing in time domain. The higher the sampling frequency, the easier for the DFT to recognize our main function and transform it correctly. Now the corresponding values of these samples are important when we are creating a function from a set of data points, because the DFT formula takes into considerations these values to transform the function from its time domain. Okay, now you are ready for a simple example on MATLAB. This is the MATLAB code for any function you want to transform it. Pause the video and take a look at it and read the green notes carefully, or save it if you like. Okay. Now let's take a look at our function in its time domain. Okay, as we can see, this is our function. We want to decompose it in the frequency domain. We want to know the frequencies and amplitudes in our frequency domain. To do that, let us plot it in the frequency domain. Okay, as we can see now it is in our frequency domain. If our process was true, then it should give us two sinusoidal waves with their correct frequencies and amplitudes plus one DC value with zero frequency. First, let's remember our time domain function. You can see that there is already a sinusoidal wave with amplitude equals 3 and frequency in Hertz equals 30. The other sinusoidal wave is with an amplitude equals 4.2 and frequency in Hertz equals 40. The zero frequency component equals 5. Now let's return to our plot in the frequency domain. As you can see, 30 Hz correspond to 3 amplitude value and 40 Hz correspond 4.2 amplitude value. The DC value is doubled here because we multiplied the transformed function by 2. Actually, after doubling we should get correct results for all frequency components except for the DC value or the zero frequency component. You should know by yourself that it is doubled. Why should we double these frequency components and take it for a half side? The reason is that the DFT assumes by default that our main function is periodic after the last point we took. As we can see in this image, the function repeated itself exactly after the last sample. This is what the DFT assumes. This effect will show in the frequency domain. If we took the other half side in the plot, it will just give half of the values on the left side and half of the values on the right side. Which means that the plot will be mirrored, thus we can multiply by 2 and plot only one side, and that's what we need for more real results. The division by n is nothing but a normalization to get reasonable values and not huge numbers. What is windowing? Windowing is a phenomenon that occurs when we take the last point in our time domain function to be a point which is not where the function repeats itself. As we said that the DFT assumes that your function is from the first point you took to the last point we took. Hence, if we took a point which is not where the function repeats itself, the DFT will capture another function that is different from our original function. Thus, it will give values in the frequency domain based on the function it captured in the time domain. Let's take a look at a cosine function with amplitude equals 3 and frequency equals 5 Hz. As we can see in this example, I took the duration to be 2.5 in our time vector, which is a point where the function did not repeat itself. Let's visualize the frequency domain now. As you can see, the maximum amplitude value did not reach 2. And it gave frequency components which are not presented in our time domain function, like the 2.8 Hz and 6.8 Hz, which are located to the left and right of the sharp frequency line. Okay, so how can we avoid this phenomenon called windowing? We can avoid it by taking the last point to be a point in the time domain where the function repeats itself. For example, in this case we can take the duration to be 1.4 or 1.2 or 2.4. Let us repeat our example by taking the duration equals 2.4 to increase the number of samples. After we did that, as you can see, the windowing is now avoided and the values are correct in the frequency domain. That is because the DFT was able to capture our function correctly. Now let's take an example with the case where we represent our function by a set of data points which are the function's range points. But first notice that when we want to apply the DFT for a function represented by a set of points, we will take these points to be the output points of our function. On the other hand, the set of data points for the dependent variable t are not inserted in the DFT formula. They are used for two reasons only. The first reason is that we cannot build a function without these domain points. The other reason is that to know the sampling frequency, which is the reciprocal of the spacing dt as already explained. We should note most of real-life DFT applications represent the function by a set of data points rather than expressing them by an equation. That's because our function may be very messy, which makes it hard to represent it by a known equation. For example, if we took a displacement function with time for a motor which is vibrating up and down roughly, the function captured by using the vibrating sensor will be a set of points. And in this way the function will be plotted based on these points captured by the sensor. Now again to our example represented by a set of points which is actually a linear function. After we finished the MATLAB code, we want to plot our function in its time and frequency domain. Let's plot them. Okay, let's take a look at the time domain function. The first point is 0 and the last point is 2 as expected. Now let's jump to the frequency domain. As you can see, the DC or zero frequency value is 2, and we should divide it by 2 mentally as we said before. The other frequency values are given with their amplitudes also. Okay, now we want to compare our results with the Fourier series results. But first, let's say some notes about our function. As we said before, the DFT assumes that our function is periodic after the last point we took to build our function. It is actually repeated from negative infinity to positive infinity with a some known period which is in our case equals 2. Here the green function is our function that we represented it in the previous example by a number of samples equals 2001, from t equals 0 to t equals 2. The red parts describe the repeated parts of our main function. This is what DFT assumes. This assumption is a great key to compare our results with the Fourier series results, because it can convert our problem to a Fourier series problem with period 2. Look at this image. This is a Fourier series problem that is equivalent to our DFT previous example due to the periodicity assumption as shown in the previous image. All we have to do is to set capital A to equals 2 and to set capital T to equals 2 to convert our MATLAB previous example to a Fourier series example. Here is the general equation for any linear function represented in this shape at the top right of this image. The equation below shows that our function is decomposed to a DC value expressed by capital A plus a sum of negative sine waves with different frequencies and amplitudes. N is an integer from 1 to infinity and it stands for the nth harmonic. Where the A capital over n pi stand for the amplitude of the decomposed sinusoidal waves which are in this case negative sine waves. Omega or W is the angular frequency which equals 2 pi over the period t capital. In our case the period is 2 so omega or W will be equals pi. Okay, now we need to check for the 2 Hz frequency value and check for its amplitude. 2 Hz correspond to 12.57 rad per second, and since the equation holds for rad per second units, we should let NW equals 12.57 rad per second. To do this, N should equal 4 since W equals pi. Now to know the amplitude of this frequency we will substitute in the amplitude term by simply dividing capital A by n pi. The amplitude for 2 Hz is now known from the Fourier series equation and it equals 0.159. Let's try another value also which is 5 Hz. 5 Hz correspond to 10 pi, now substitute by 2 over 10 pi that will equals 0.0636, you can try any value you want and compare it with your plot. It should give correct results. Okay, what about the DC value? It is simply capital A over 2 as shown in the formula which will equals 1 in our example. Okay. Now let's take a look to our plot in frequency domain for our example to compare the results with the Fourier series results. Here you can see at 2 Hz we get an amplitude equal to 0.159. At 5 Hz we get an amplitude equals 0.0636, and the DC value is equals 2. This confirms my words when I said that we should double the amplitude of all frequency values except for the DC or zero frequency value. Okay, now let's take an example for a random set of data points instead of the simple linear function example we just took. We will generate 4001 random values by the help of MATLAB code without negative values. Pause the video and watch the MATLAB code carefully just to figure out the basic steps to plot this function in its time and frequency domain. Okay, let's take a look at the plot. The upper side shows the function in its time domain. It looks really messy and complicated. If we can transfer it to the frequency domain as in the bottom side, that will be more comfortable. See how many frequency components are there. We can observe that the dominant frequency component here is the DC value which have the higher amplitude. All other frequency values are oscillating at lower amplitudes. I should note that when you are using a set of data points there is no place for windowing to occur. Because you already built a complete full function with a set of data points that is assumed to repeat itself after the last point you took. On the other hand, when we took a cosine function it was really important to avoid windowing. Because the cosine function is already periodic in nature and it would really matter if we took the last point to be a point where the function does not repeat itself in its accurate shape. Another note I should tell you when you are building a function from a set of data points is that you should be careful to choose the sampling frequency and time vector by such a way that the time vector length matches your built function length, exactly as we did in our example. Now let's talk about power spectrum in a very shortcut. Power spectrum just means how much power each decomposed frequency component has. It simply equals the amplitude spectrum squared. If you're interested more in energy and power of signals, you can check that later. Now let's take a very simple example for plotting the power spectrum values with their corresponding frequency values instead of taking the amplitude spectrum values. Okay. Here is our function, which is a cosine wave with one frequency component equals 5 Hz with an amplitude equals 3. As you can see, the code is exactly the same for the amplitude spectrum case with one easy additional step. That is to multiply the amplitude spectrum value with itself and to plot it with the frequency values measured in Hertz. Now let's look at the plot for our function in frequency domain. As you can see, the 5 Hz correspond to a power spectrum equals 9, which is the amplitude spectrum squared. You may take more than a frequency component and a DC value for sure, with noting that the DC value is doubled and squared. So you should mentally divide it by 2 and then square it to get the correct power spectrum result. Power spectrum applications are found in filtering noisy sounds, for example in the field of sound signal processing. I hope you enjoyed this video and became satisfied with the discrete Fourier transform topic. I will also provide a link in the description box to see some of the real-life DFT applications. Thank you for watching and Assalamu alaikum.